Welcome to another episode of Down to Earth. I'm Eric Edelman, your host, and on tonight's episode, we're going to be talking about the countdown to solitude. Particularly, we're going to take a look into our future and what possibilities it could hold. And so, we're going to take a look at our future from the perspective, actually, of space travel. So, we have our own solar system, which is one stellar system amongst hundreds of billions in our own galaxy. And our galaxy is one amongst at least hundreds of billions in our own universe. And we're starting to take trips just outside of our planet. So far, we've visited the moon. We're thinking of colonizing Mars. We've sent unmanned spacecraft even further to Pluto and beyond. And as we continue to develop technology that allows us to travel further and further out into the universe, we'll have new frontiers to explore. And perhaps one day we'll even leave our own solar system and visit planets around other stars. Perhaps one day, even further into the future, we'll visit planets and stars that belong to a galaxy beyond the Milky Way. And maybe we'll visit places like we're looking at in the Slooh telescopes tonight. Particularly, we're going live from the Canary Islands today, looking at a spiral galaxy right there in the center of the frame. That's M94. It's a galaxy that's 16 million light years away, so quite a big distance when we're considering the terms that we've been able to travel in our recent history. But hey, it's still maybe not out of the potential of human potential. And so, looking at this galaxy, looking at this thing that's so very far away from us, but is still relatively close in terms of the gigantic scale of our own universe. The question that we're sort of going to ask here is how far can we as human beings go? How far can we travel? And if we continue to improve technology through centuries, millennia, millions, or billions of years, will we get to the point where everything and anything is accessible to us? Can we get anywhere in our universe if we just try hard enough? Are there limits, maybe, to even the ultimate advances in technology that we can make? Just where exactly can we get to? And so the answer to this question is we're not quite sure yet, that there might be some limits. Actually, they probably very likely will be some limits, unfortunately. And that actually has to do with some of the particular behaviors of our universe. So physicists actually describe this universe as springing forth from a point of infinite density, a big bang, as it will. We're seeing actually a great timeline here where it goes from right on your screen to left on your screen is how time passes here. So a point, and then galaxies start to occur, and then we start to see things that are much more familiar to us and our present time in the universe. And so at the Big Bang, this point, it expanded, and it's continuing to expand even today, as it's become the universe that we know, that it has not stopped expanding and will continue to expand even into the future. And so we actually have a tool that actually is on Mathematica that shows us sort of what it looks like being in this universe that is constantly expanding, a sort of simulation, as it were, of where different galaxies are now and where they are in the future. And so what we see here on the screen is there's a number right in the center of that square, and that's us. That number is our galaxy. And then the number surrounding it, those are different galaxies that we have nearby to us and maybe a little bit more distant to us. And so by starting the simulation, we can see what happens as the universe expands. And so now the shady gray areas where the numbers first initially were, that's where they were. And then where the numbers are moving, that's where they're expanding out to in our universe. And so from our point of space, we're seeing everything sort of moving away from us. And any other number that you picked, if you looked at any other number and had that as your reference frame, as the point that you were seeing from, it would look like all the galaxies were spreading away from that number as well. So what exactly is happening here, though? Why is the space between us and everything else getting bigger? Why is there this expansion that is occurring? And it actually has to do with the composition of our universe, what it's made of. And so we actually have a sort of a pie chart that shows you sort of what different materials are made of in our universe. And it's actually pretty surprising because some of the stuff that we're made of is the smallest piece of pie in the pie chart. Like right there, the atoms, it's sort of at the top left of your screen. The 4.6%, that's the stuff that we're familiar with. It's made us up, it's made our planets up, our stars up, just the familiar baryonic matter that we are used to. That's the minority, the extreme minority of the stuff that is out there in our universe. And then after the normal matter that we're used to, then we have dark matter. Dark matter is that green slice of the pie that we see there. That makes up, I believe that's 34% right over there, 24%. And so dark matter is really interesting because it's what we know is there, but we can't actually see it. And we know it's there because of what we can see within different galaxies in our universe. There's a really actually fantastic video we have of the rotation rates of galaxies that can really show us what exactly is going on in both in these cases. So we see on the left and right two galaxies that are rotating, two spiral galaxies maybe similar to our Milky Way. And so how a galaxy rotates really tells us how much matter that there is in that galaxy. And so on the left shows a galaxy and how it would rotate if the matter in the galaxy that we can measure, all of the regular matter that makes up you, me, planets, stars, things like that, that was all that was there in that galaxy. And that would mean that the further out you went in this galaxy, the more distant you were from the center region, that bright center spot, then the slower things would go. The rotation would sort of peter out by the edges of the galaxy. And you can see that by looking at this rotation, and you can see the edges sort of lagging where the center's a lot more active. And then on the right side, sort of by my box here in the video, is the example of what happens if there is a little bit more matter in this galaxy than we can see, more matter than we can measure in terms of the stuff that makes us up, and in terms of what makes planets and stars up. If there's more stuff out there that we can't really see, if there is that stuff, which we're actually calling dark matter, then a galaxy will rotate in a way that it won't get slower the more further out that you go in that galaxy, that it will all be sort of rotating at relatively the same rate, even at more distant spots in the galaxy and even at really close spots to the center. And that's what we see with most of the galaxies out there, that they're all sort of rotating in a way that betrays that they have some extra matter that we can't see or measure. And that's what we say is dark matter. And there's so much of it compared to the regular stuff that we know about. We know that there's so much because there would need to be just an extreme amount to make these rotation rates of these galaxies that we see out there. It's a very, very strange phenomenon. And then after the dark matter and the regular matter that we see here, then we have dark energy. That's the last piece of the pie that we have, and it actually makes up a huge majority of the matter that we have, or the energy that we have in our universe, what composes our universe. It's dark energy is an energy that is uniformly everywhere throughout space. However, at the same time, it's around in very low densities that would make it really difficult for any of our detectors to get a reading on it. So even with the low density, it still makes up most of our universe just because it's absolutely everywhere. And even in the dark energy empty void, even in those dark empty voids where you think there's nothing else, there's dark energy there between galaxies and clusters of galaxies. And it is in these places that it is particularly important to what we're talking about here today. So like in this image where we're seeing the Hubble Ultra Deep Field, incredible image which shows a vast array of galaxies, some very deep into the furthermost reaches of our universe. Those black spaces, they're always going to be getting bigger and bigger in size. The emptiness is expanding. And even though that emptiness is expanding, there are certain places that are able to fight off that expansion, why we have our galaxies and things like that, because gravity actually is something that is able to overpower some of this inherent expansion of the universe. And so that's why our stars and our planets are able to stay in orbit around each other. The galaxies are able to, when they're at close distances, even orbit each other as well. So gravity here, it really helps to slow down or stop this expansion, but it can only do so much. It holds together the massive stuff, the galaxies, the galactic groups, but everything else, it continues to fly away from us, to get further away from each other. And the further away it is from us, the faster that it recedes, because there is more empty space for dark energy to push apart. There's more emptiness to become even more emptiness. And so let's actually return back to the Mathematica simulation that we just saw a little earlier here, because that can show us actually how that works in terms of the things that are distant becoming even more distant from us. And so we see the numbers going away from us. But if you look at the numbers closest to the center versus the numbers more further away, you're seeing that those numbers further away are moving away much faster than the numbers that are closer in. So at the further away you get, the further away those galaxies are going to get at an even more extreme rate. It just keeps getting more and more extreme the more and more distant that you are. And so going sort of back again to the Hubble Deep Field, it's great to look at those galaxies because that gives you a great example of the smorgasbord that's out there. We're seeing some closer galaxies and some that are really further away. And some of the very smallest pinpricks in this image are galaxies that are just so far away from us that space is really getting bigger and bigger at a very extreme rate. And as space expands between us and them, the light that we see from them gets shifted to longer wavelengths or redshifted. And so we see a lot of those galaxies that are much more distant from us as very red things compared to some of the more closer galaxies in our universe. And these really red galaxies, it can get to the point where these reddened objects are so extremely far away that they will be receding from our view faster than the speed of light. So that's pretty crazy. There will be certain distant galaxies that we see light from here today that we won't be able to see any longer in the future because they're receding so far away, so quickly away from us that even light will not be able to make up the difference, will not be able to travel at speeds that will get us that light, that information. And so getting back to us and space travel, when it comes to traveling to some of the most distant objects away from us, this issue here can pose a problem. The fact that certain very, very distant galaxies are traveling away from us as faster than the speed of light. Because as far as we know, the speed of light is the very speed limit of the universe. And since parts of the universe are flying away from us faster than that limit, there are places that we can never really reach. Like as we see here, our galaxy is one amongst many, and there are very many distant objects far beyond it. Even if somehow we were able to master the speed of light travel, there would still be galaxies that would be too far away for us to visit. Even the speed of light, even getting that amazingly fast, still can't get to some places. And so just recently, astronomers were actually using the Hubble Space Telescope and noticed that the universe is expanding even faster than we originally thought, about 5 to 9% faster. And so NASA reports that this means that the distance between large cosmic objects will double in 9.8 billion years. So this is a long time, but this is a lot of distance as well. It's a big increase. Something 10 billion light years away from us today could be 20 billion light years later. It's an extreme increase. And so what does that mean for us? And what distant worlds could we potentially visit? So, well, let's think of the scale of our hometown. So our solar system, that is actually located in the Milky Way galaxy, which is part of the galactic group called the local group. And so, yeah, we see the local group here. And this is about 10 million light years across. So it's a huge group of galaxies, but at the same time, it's still distances that we can maybe comprehend in terms of space travel. And so this group is made up of 54 galaxies, and out of which we're actually one of the largest alongside Andromeda. So the great thing about the galaxies here is that they're actually gravitationally bound. And so remember a little bit earlier we were talking about how gravity can sometimes defeat that expansion of the universe, and so can keep these things in place. And so this means that the gravitational interactions among these galaxies, they're actually strong enough to keep them bound together as a group. So they're not going to be receding away from us as the universe expands. So beyond this, though, beyond the galactic groups, we have the galaxy superclusters. These are massive clusters of galaxy groups. So a bunch of galaxy groups all together in one massive supercluster. And so these superclusters, they can be considered some of the largest groupings of stuff in our universe. And here is part of our local supercluster here in the Virgo group. The local group is actually, it's part of the Virgo supercluster that we see here, which is in turn part of the Laniakea supercluster, which is 520 million light years across and full of around 100,000 galaxies. So this is an amazing number of galaxies here. But the unfortunate thing is about superclusters is that these clusters are not gravitationally bound. And so the groups of galaxies in this cluster are actually, they're going to be moving away from each other as the universe expands. And so with this thought in mind, let's look at the live Slooh imagery that we have coming in here. I believe we're looking at the M51 galaxy right now. That might be live. But we have a live galaxy that we'll have from the Canary Islands scopes. And oh yes, it is M51, the Whirlpool Galaxy that we're seeing. This is another live image straight from the Canary Islands, courtesy of the Slooh scopes. And M51, it's part of the M51 group, which is part of the Laniakea supercluster, which is part of the local group is also where we are, is part of the Laniakea supercluster. But we're in different galaxy groups. M51 and us, we're in different galactic groups. And so we're part of the same supercluster, but we're not gravitationally bound to each other. So this M51, the Whirlpool Galaxy, it's not going to be moving toward us. It's going to be moving away from us with the expansion of the universe. This is going to be a galaxy that it would be very, very tough to get to, and will be even tougher with every second that passes, is the unfortunate truth of that. And this is just an object within our own supercluster. There are many superclusters we know about there in the observable universe. The observable universe is even huger than our supercluster schematic that we have. And even more distant galaxies and other superclusters. Oh, here is our observable universe imagery that we have here. And so it's easy to feel dwarfed by this because there's just an incredible amount of stuff that we have in our universe. This is something that's 93 billion light years across. Extreme distances. And so a lot of stuff here will be moving away from us very, very quickly. And so taking into account, this is 93 billion light years. We could only travel about 15% of the distance that our observable universe is if we were traveling at the speed of light for the entire length that the universe has been around, for the entire age of the universe up to present. We could have only traveled 15% of this distance. That's how massive this is. And so the speed of light compared to what we're used to is marvelously fast. But with all this taken into mind today, it still does limit our maximum potential. Of course, we did talk about possible exceptions like wormholes in an earlier episode of Down to Earth. So never say never, I suppose. But I would probably say it's not going to be very likely in certain cases when it comes to some of the most distant stuff out there in the universe. So we are limited here. But this does not mean that our frontiers are not vast, because they are. We haven't been outside of our own solar system yet, and still we have the entire Milky Way galaxy left to explore. And in our galaxy alone, again, there are hundreds of billions of stars. And we believe, just as we've been able to measure a lot of exoplanets around some of the nearest stars by extrapolating off of those measurements, we are pretty sure that a majority of the stars in our galaxy have planets around them, have at least one planet around them. And chances are some of those planets are going to be interestingly habitable, potentially already inhabited, say, by some other alien species. And so there's so much to explore in our own galaxy alone. But if we get tired of exploring those hundreds of billions of stars in our own home galaxy, then we also do have those galaxies in the local galactic group that aren't going anywhere. Those galaxies are all gravitationally bound together. They're not leaving us just yet. And so some of them are actually even getting pretty close to us as we speak, moving in our direction. Like, for example, the Andromeda Galaxy, which is on a collision course with our galaxy and will bring its approximately 1 trillion stars to us in about 3.75 billion years. And if we end up getting tired of Andromeda Way, or whatever we end up calling the future amalgamation of Andromeda and the Milky Way, we can explore the other 50 or so galaxies in our own local group. Most of them are a little bit smaller than the Milky Way and the Andromeda. I will admit that, but these known dwarf galaxies, they have several billion or so stars. That's still a lot of stars. And so getting beyond our local galactic group, though, beyond these 53 galaxies, that's the part that might get a little bit tougher. But even though there is that potential limitation there because of how our universe is expanding and how astronomers are still learning more about how it's expanding, even though there is that limitation, there's still so much here to explore in our own very own backyard. And I personally don't really see the limitation that we have in terms of what we can explore as much of an issue because there's just so much out there. I mean, think about it. There's trillions of stars in our galactic group, our local group, just that place alone. And if life exists outside of Earth, somewhere out there in the universe, then chances are that at least some of it will be within our reach to travel to. Instead of thinking about what we can't do in terms of space exploration, I think it is marvelously fun to think about what we can do. And we're only just getting started because, again, we've just been sort of tiptoeing around our very own solar system. So if we as a species keep on surviving, we have billions of years of spacefaring adventures in store. And I really do think it will be a grand old time. So the question that I would like to leave you here with today is, where would you like to see us go? How far would you like to see us be able to get to? Would you be satisfied with humanity staying within our local group of galaxies? Or are you determined to see us travel beyond that realm? Like, would you like to see us get to M51, even though it isn't in our local group? That galaxy there, it's in a different group, but it is within the same supercluster. So maybe if we tried hard enough, would it be close enough? Would we be able to beat the expansion of the universe with the expansion of our own technology? Where do you think the limits should be? Should there be any limits? How would we overcome them? And so you're welcome to chat about this thought in the chat box if you aren't already doing so. Where the chat box is, if you're watching the show live, it's either to the right of it or right below it, depending on your browser. And I love to see whenever members are talking about different things that interest them. So if this is a topic that interests you, welcome you to go at it. Love to see what you're thinking about that. But with that being said, that is it for tonight's show. Thank you so much for joining me here for another episode of Down to Earth, gazing at the universe and wondering what's out there. We're always going to be here live on Tuesday nights on Slooh.com. Thanks again for joining me.